So we are going to start with electromagnetism today. I think last class Astrophysics 5 was shared with everyone. And this file I cannot actually share with you guys in WhatsApp, but I'll again try after the class. Okay, I'll give you guys a blank file and also the filled up file. So we're going to start with this question. Says the diagram 1 shows two magnets, north and south. Draw the field lines on diagram 1 to show the uniform magnetic field line in the shaded region between two poles. Right. We always understand that field lines are going to be, they're giving you 2 marks. 1 mark for that uniform distribution, like all the, the distance between all the lines are going to be same, and all the line has to be parallel, and they also must have the same direction. Okay. So you have to make sure these 3 things are correct in your diagram. One is your distance between lines. Then second point is that all the lines should be parallel, and your direction. Okay, that gives you 3 marks. They're giving you 2 marks over here. And then again, you don't always have to measure this with scale, like if the distance between 2 lines are always same or not. First thing you will do using a scale, first you'll do the outer lines first. Okay, these are the outer lines. Right, then you draw a line exactly in the middle. That kind of different, creates 2 different regions, and then you just draw another line in the middle, and then again another line in the middle, right? That way you don't have to exactly measure all the distances. This is how random, by eye level, they kind of look that they all have the same distance. It's just an easier process to draw the parallel lines, and then all of them should go from north to south, right? So just draw the directions then. This ensures all these 3 points, so you're going to get full marks for this uniform magnetic field lines. Any problem from this part?
No, miss.
Okay, then if you move on, the diagram 2 shows a current carrying wire in the uniform magnetic field between the poles of a magnet. This is a U shape. Obviously, we're going to get uniform magnetic field lines in this direction, right, from north to south. The arrow on the wire shows the direction of the current. Draw an arrow on the diagram 2 to show the direction of the force on the wire. I have to represent, I will use the Fleming's left-hand rule to represent that force, right? In Fleming's left-hand rule, if you understand that your third finger indicates the direction of your current, so your third finger should be pointed towards the right-hand side. And then again, your second index finger indicates the direction. Oh, wait, sorry. My mistake. Third finger indicates the current, right? Yeah. And your field line is represented by the second finger. So in this situation, if you indicate the current over here, like third finger should be pointing to the screen, to be honest. I mean, if you think of this as a page, then your third finger is pointed towards the page, into the page, and your second finger is to the right-hand side, and automatically your thumb will point towards the downward. So over here, you just have to draw a downward force. You don't actually need to draw this line over in this case. You just only have to show that we have a downward force acting on this wire, right? That's your downward force. Just have to label this is as your force. Right. Is this clear? Two marks for labeling the arrow's direction and labeling that arrow. Like this is force and the downward direction. They're giving you 2 marks for this. Do you guys understand how to use a Fleming's left-hand rule and how your thumb is pointing towards the downward side? Any question regarding that?
It's famous.
Then if we move on to the next page, then we have this is kind of a motor effect or generator. Figure 3 shows a rectangular loop of wire carrying a current in a uniform field line. Explain why the loop starts to turn but stops when the loop is vertical. When it starts to turn but stops when the entire loop is vertical. Okay, in this case, you have to think about, basically there's explain why the loop starts to turn but stops when the loop is vertical. That means whenever, like, A, B, this is how the loop becomes. Right, this is your AB and this is your CD, right? AB will be on top of CD, and in this position, it will just stop rotating, and then again after that, I think it will go back to the other direction, something like that they're saying, because it starts to rotate in the vertical plane, but whenever, so in the horizontal plane, but obviously it's rotating, so at some point it will reach the vertical plane where AB and CD are in the y-axis, and AB is above CD. In that arrangement, everything, the loop stops to turn in that situation. The reason is that we have to first explain that why would the loop start turning in this position, like in the horizontal position, why would the loop start turning in that case? Because obviously the current carrying wire, or in this case, we should consider as the current carrying coil. The current carrying coil has its own magnetic field line. So whenever this current carrying coil's magnetic field line is interacting with the field lines of the permanent magnet, right, perpendicularly always, this exerts a force on the wire, specifically on AB and CD, right? So if I assume that current is moving in this direction, for AB the current was moving in the upward direction, and for CD the current was moving in the downward direction. So in that case, obviously still now your field line are moving to the north and south, from the north to the south. So for AB, for this section, we have a downward force, and for CD, we have an upward force. So in that case, obviously over here, the entire coil is now exactly in horizontal plane, right? This is how the entire coil looks now. For AB, we get a downward force. For CD, we get an upward force. So the coil will now start to turn in the anti-clockwise direction. So after rotating for 90 degree, the coil will be in this position. This is your AB and CD. After 90 degree exactly, the coil will be in this position, where CD is on top and AB is on bottom. But and in that case, what happens this time? The current, like like over here, no force will be exerted in this situation. In this case, wait a minute. Yeah. No, in that case, it must rotate exactly 180 degrees. But they're saying it stops when the loop is vertical entirely. The forces in opposite direction for the first one, that for AB we have a downward force, for CD we have an upward force, and then that's because obviously the current was in opposite directions for around this loop. But there's actually a problem. Usually for your generators or motor effect, right? We have split rings brushes, right? Carbon brush and split ring commutator. Those are actually responsible for swapping the directions of your pole, right? So after 90 degree anti-clockwise rotation, right? This is how your entire field line would look. This is how the loop would look. This is your A, B, and CD. Right, if that's the case, the current is still moving in the upward direction for AB and downward direction for CD. In this case, what happens over here, whenever the loop becomes vertical, the magnetic fields of the loop and the permanent magnet's magnetic field, they are going to be parallel to each other. They will not cut each other. They will not cut each other perpendicularly or with any slight angle. Now they are going to be parallel. If they are parallel, so obviously in that case, we don't have any force. According to Fleming's left-hand rule, we get zero force when field lines from different sources are going to interact parallelly, right? So at the vertical position, all the field lines are going to be parallel to each other, and that's why we could not see any force exerted onto the loop. If there is no force exerted on the loop, so obviously the loop will not rotate or will not move at all. It will just stop at exactly at the vertical position. Is this clear? Any question from this part?
No,
It's
miss.
famous.
So we just have to write, first thing is that why would the loop start rotating when it is in the horizontal position? You just have to say that current carrying the coil lens of the magnet. So you don't need to write according to Fleming's left-hand rule over here. You can just see that direction rotating the coil in anti-clockwise direction, right? Anti-clockwise direction. And what can we see? Then we'll see that since there is no split ring commutator to stop the current in the, so to swap the swap the current directly. Actually, in the vertical, we will have one. In that case, this is how horizontal impact in the vertical plane. We have current in this direction. In the vertical plane, what exactly happens? Like this is your CD and this is your AB, right? In this case, CD and AB, for both of them, there will be a downward force acting on them. And in this, and over here, both of them are exactly perpendicular in this situation. Both the wires are entirely perpendicular. And in that case, what happens? For this CD also, we have a downward force acting in them. For AB also, we have a downward force acting in them. So force is acting in them, but we need to, if I want to rotate them, I need a horizontal force also, right? But there will be no horizontal force. So force doesn't change the direction. So at the vertical point, both the forces will create a same direction. If both of them are going to act in the vertically downward direction, right? But to make it rotate in this direction, we need some horizontal forces also. That's not there. That's why there is no moment at the vertical point, and eventually if the coil will not rotate at all. So we can see since split ring commutator, this to swap the current direction, then or also we can say which makes the or which, hang on a minute, we can just say So there is no net moment. Yes, we can say that. So net moment to rotate the coil. Right? That's the final answer is supposed to that. Is this clear?
Yes, miss.
Amra, any question from your side?
No, miss.
Then we'll move on to the next part. So the diagram one shows a generator inside a small wind turbine, and the generator is connected to a lamp and the windmill blades. Okay, so there's this lamp. There are brushes now. Split rings also available. There's an ammeter, permanent coil, then permanent magnet coil, and then that fan. When the coil rotates in the direction of the arrow, okay, that means in the clockwise direction, the ammeter displays a small current. Explain how the generator creates this current. We understand they're giving it 2 marks, right? So we understand that over here, what happens when that fan rotates, as a fan is connected to the coil will also rotate. And if the coil is rotating, then obviously there is some linkage happening, like flux linkage is happening over here because the current carrying coil's magnetic field will be perpendicular to the magnetic field of your permanent magnet, and therefore because of this flux linkage, a voltage will be induced in this circuit. And if a voltage is induced in this circuit, obviously a voltage induced means a current is now flowing through the circuit, and therefore it shows a current in the circuit. So the 2 marks over here, you just have to say that as the coil rotates to the magnetic field, there is a flux linkage which induces a voltage that shows a or that creates a current flow in the circuit, right? And yeah, that creates a current flow in the circuit. We can also say AC current supply because we have like split ring that will continuously change the direction of your current flow, but we don't have to think about all those things because as they're only giving me 2 marks. If they were like giving me 4 marks, I would include all those details also. So I'm just going to write that coil rotates through magnetic fields coil rotates through the magnetic fields that induces voltage and voltage to the magnetic field that induces voltage which creates a current flow in the circuit, right? That's enough to explain this concept. Then if I'm moving to this part, the generator in the wind turbine acts as an alternating current power supply. Diagram 2 shows the electric circuit containing generator being used to charge a mobile battery. There we have a generator, then diode and everything. The direct current is needed to charge the battery. Explain why there is a diode in the circuit because I know diode is what? Diode only causes the current to flow in one direction. So diode kind of like maintains that thing, right? So I have to just they're giving me 2 marks. So I'm going to say that yes, direct current is a current only is a current that flows only in one direction, and diode allows current to flow in one direction. Like diode is only fitted over here to make sure that also current is over here only traveling in one direction, right? That's the only thing you have to write. So we just have to say that DC only flows in one direction and diode Right. This too is enough. We are explaining what DC is, and then again how and why we're supposed to use a diode in this DC circuit. Other than that, it says to explain how the current in the battery will change if the wind speed increases. If the wind speed increases, in that case, how will the current in the battery will change if the wind speed increases? 1 minute. The generator in the wind turbine acts as an alternating current. Diagram 2 shows. So this one is not related to diagram 2 then. It says explain how the current in the battery will change if the wind speed increases. Diagram 2 shows the electric circuit containing a generator being used to charge a mobile battery. Yeah, that's not related to this diagram then. The wind speed increases, then what? Then the coil will rotate at a faster rate, right? So if coil rotates at a faster rate, there will be more flux linkage, right? For more flux linkage, a higher voltage will be induced. A higher voltage means a higher current. So we just have to write all those things over here. That in this case, at high speed, faster through the magnetic field lines, increasing flux linkage, therefore creating not creating mistake, therefore inducing large voltage which causes higher current for the cycle, right? Is this clear? Any question from this part?
No, miss.
Okay, then that's it. If we move on to the next one, it says that the mean voltage across the battery is 7.2 and the battery gains 14 kilojoules of energy in 8400 seconds. Calculate the mean current in the battery. So we have energy, we have time, we have voltage. We are going to use, they're giving you 3 marks for this. That means write down the formula that we are using. I'm actually using that power equals to IV, but I can break down power also in terms of energy over time IV, right? So from this part, if I make I the subject, it will be energy divided by VT. Yes, VT. So we get how much? 1400, sorry, 14,000 it will be. So we have 14 10 to the power of 3 divided by 7.2 into 8400. So now we get, sorry, 14 into 10 to the power of 3 divided by 7.2 into 8400. And we get the answer as 0.2314. That's a very big value. But I can see every data in here was given in two significant figures, right? Or in the question, every data was given in two significant figure. And in that case, we can consider writing it as 0.23 amp. 0.23 amp. So we get 0.23 amp. That's it. Now, so far, the questions we have done, there was no repeated question actually. It's explain how the generator produces a current. Yeah, you can think of this as a repeated question, but this also doesn't contain the maximum number of points, so I will not suggest memorizing this question, but explain why this is a very important question. Like, it was quite different. Usually, we always consider that after every half turn, the rotation stops, and then again it kind of reverses back to the original. It reverses its direction. But this was different. Over here, without the split ring commutator, It will only rotate 90 degrees and then again stop, right? That was a different idea. So this is not going to be a repeated concept, it's a different concept, very important. Other than this, all the questions that we have seen are not repetitive and also not that much, they are repetitive, but not that much, that they don't contain all the marks 10 points here. So I don't want you to guys to memorize anything from this part. Okay, then if you move on to this case. This one says diagram 1 shows the magnetic field lines near the south pole of the bar magnet. Draw 2 arrows on the field lines in diagram 1 to show the directions of the magnetic field lines. I mean, I just have to draw 2 arrows. I mean, the lines are already there. It's going to be in this direction. Oh, wait, no mistake. It's the south pole. So field lines are going to enter the south pole. Hope writing these 2 arrows are enough. Then again, which of these is attracted to the bar magnet if placed in the magnetic field? Copper, nickel, plastic, zinc. Plastic obviously will not be attracted because plastic is just a non-magnetic material. That will not attract. This will not attract. Then in between nickel and zinc, these are transition metals. Transition metals do not actually have magnetic properties, but copper is a specific metal. Wait, copper is also a transition metal, right? 1 minute. So this is attracted to the bar magnet if placed in the magnetic field. Yes, zinc and nickel are actually not, nickel is actually a magnetic material. Copper and zinc are not magnetic material. Right? Let me just check one minute. Just a minute. Over here, zinc and copper are not magnetic materials. That's because they don't have any extra electrons. Usually for any other object to attract the metals over here, they must have your electronic configuration in such a way that at least one of the electrons will not have its pair. For copper and zinc, they are all fully paired elements. That's why they will never be attracted to other magnetic material. But nickel will have an extra pair who is not attracted to your, so who doesn't have any pairs. So nickel with an unpaired electron, that's why it will be attracted to your magnetic materials. So only nickel and not copper and zinc. So I'll just write this down, this and this. Unpaired electrons, right? Also, another thing is nickel or transition metal. Nickel is also considered as a transition metal, so we cannot assume that all transition metals are going to be non-magnetic material. Only copper, zinc, aluminium, these are not magnetic material. Otherwise, nickel, iron, they are also your transition metals, but they will be acting as a magnetic material. So we can see the strength of a magnetic material. Wait 1 minute. Another thing, I know nickel is a metal, right? Now, nickel itself, it doesn't have any magnetic property. But when you place this nickel inside the magnetic fields of another permanent magnet, then I see that this nickel is attracted to the other magnet, right? So what type of magnetic material is nickel then? Magnet, it only shows the magnetic properties under the influence of other magnetic materials. If other magnetic material was not near nickel, nickel will not show any magnetic properties. Nickel only shows one magnetic property, that is attracted, right? Attraction. It only gets attracted to other magnetic materials, but it cannot attract other nickel particles because nickel itself is not a magnet. It only acts as a magnet as long as we are placing that inside the magnetic field lines of another magnet. So what type of material is nickel then? Is it hard or soft, or what type of magnet it is?
It's soft.
Soft only considered as that when we consider about your electricity, right? If I'm applying electricity to them, as long as I'm applying electricity to them, they will able to hold their magnetism. And as soon as you cut off the electricity supply, they loses their magnetism. Those type of materials are known as magnetically soft material, right? And hard is steel. For example, if you cut off the magnetic electricity supply, they will still be able to hold on to their magnetic properties for a long time, even without the electricity supply. This one doesn't actually require electricity. This one only acts as a magnet under the influence of other magnetic materials. They are known as induced magnetic particles or magnetic materials. Right? So nickel is an induced magnetic material. Is this clear?
Yes, miss.
We are under the influence other magnets. And soft and hard magnetic material, those are just electromagnetism when we're differentiating in between them, right? Soft and hard is for electromagnetic materials. The strength of magnetic field line changes as the distance from the south pole increases. Explain how the magnetic field lines show this. Explain how these magnetic field lines show this. I'll be able to show this by the distance between the magnetic field lines, right? So the magnetic field lines move further apart from each other, showing weak field strength and also the density, that was a density. You can say that field lines per unit volume also decreases, right? For a certain section, we will only have smaller field lines, and again, that will mean the same. So we can say that as you move further from North Pole, the distance between line increases, showing weaker field strength. Field line distance between field line increases. Number of field lines also decreases. Per unit area, right? Eventually, both of them, the distance between the field lines and also the like for a certain section, if you have less field lines in between them, obviously then the density also decreases. We can also see that density decreases, or we can also see that field lines also decreases per unit area. They both indicate that we have weaker strength, right? The field strength over here will decrease because of these two regions. We have the maximum point here as field lines increases, the distance between field line increases, and also your field lines per unit area decreases, right? Both of them indicate the same thing. So that was it for this part. If you move on to this section, the diagram shows a small piece of iron that has been placed in the field lines of this magnetic field, and the piece of iron becomes magnetized when placed in a magnetic field. Explain why the piece of iron experiences a force towards the south pole of the bar magnet. You may add two. You may add to diagram 2 to help you answer. So I can add something to this diagram too. if your iron is being attracted to these permanent magnet, so only attraction can happen if the front face of this iron, like this is the front section of the iron, if the front section of the iron is acting as a north pole, right? Because opposite poles attract each other. So I can just draw this, and then I can draw the field lines going in this direction. So finally I just write that the front face of the iron is acting as a north pole, or I can say that there is a north pole in the so there is a north pole induced on the front face of the iron, and as opposite poles attract, so that's why the iron is attracted towards the iron or towards the permanent magnet. So we can see that a north pole is induced a north pole is induced on the front face of the sorry, in the front face of the magnet, so on the front face of the iron. And as opposite poles attract, iron moves towards the magnet, right? That's your final answer. Then again, if we see that a student suggests the piece of iron is now a permanent magnet, explain why the student is incorrect. We have to say that it loses its property as fast as we remove it from the magnetic field lines, right? So this can be considered as an induced magnet, and we got the right? Well, you can also write iron is a soft magnetic material. The mark scheme will allow the soft magnetic material here. So for nickel also, if we start, I wrote this as induced magnetic material. We can also consider these as soft magnetic material. Okay, I think it's better to not consider them as induced magnetic material. It's better to consider them as soft magnetic material. So we'll just write that iron is also behaving like nickel. So we can see that first I'll explain that why is it not a permanent magnetic material. We'll see that as soon as you remove the iron from the magnetic field, it loses its magnetic property. So this is a soft magnetic material, not a permanent one. So I'll say that as soon as it is removed from the magnetic field lines, loses its magnetism. Therefore, it is a soft magnetic material, right? That's your 2 mark for this question. Then this is a repetitive question. You can memorize this one, but then again, that question is important. Wait, this is also a repetitive question, right? You can memorize this one. Other than this is also a repetitive question with weaker field lines. And yeah, that's it. Otherwise, nothing exists to be given. So we're done with this question. So we're moving on to the next one. This is first part is related to your nuclear reactions, but other parts are going to be entirely for magnetism. Moving it says the diagram 1 shows the stages of electricity generated in a nuclear power station, and nuclear fission takes place inside the reactor of the nuclear station. Give the name of the fuel that could be used for the reactor, and it's either uranium 235 or plutonium 239, right? So you can just write U 235 or plutonium-239. You can just memorize any one of them. Usually uranium is accepted. The plutonium is also in the notes section, so we will also accept that part. And if we move on, it says that energy is released from the fuel in the reactor by nuclear fission. Describe the process of nuclear fission that takes place inside the reactor. It's always your what? 4 marks they're giving. Right here. Describe the process of nuclear fission that takes place inside the reactor. It's a chain reaction. So we can say that a slow-moving neutron is absorbed by that parent nucleus, makes it unstable, and it splits into dotted nuclei, that is barium and krypton, and also it produces what three more neutrons, right? And energies. The three more neutrons will actually be absorbed by other uranium nucleuses, and it will actually continue the process, creating a chain reaction, right? These are your 4 marks. So I'm just going to write this down, that a slow moving neutron is this one. And three neutrons. Other parent nucleus. These neutrons are going to make other parent nucleus unstable to further initiate the fusion. This creates a chain reaction. Chain reaction, right? These are your 4 points. And by the way, this is again repetitive question. Whenever they ask you that what is the answer for the nuclear reaction, the answer is always going to be C, right? If you have to understand, the masking points here are absorbed by parent nucleus, unstable, then splits, then you have what are the products you get and how the products are going to be initiating the chain reaction that make the parent nucleus unstable, and then again referring to the idea of chain reaction. So this is a 6 mark point, but obviously if you write those 6 marks marking point for 4 marks, they'll not obviously cut your marks, right? So I think this much is enough for 4 to 6 mark question. Then again, if we move on to the next part, a high pressure steam transfers energy from the reactor to the turbine, and the turbine spins as the steam passes through it. Figure 2 shows a simplified generator connected to the turbine, and that's your case. Okay. Says that explain how electricity is generated by the generator, right? So basically, whenever we actually use the energy from the nuclear reactor to boil water to convert it into steam, and whenever we pass that steam at high pressure onto that generator, onto the turbine rotates. The turbine is connected to a with that permanent magnet and coil, and whenever the turbine rotates, the coil will rotate through the magnetic fields of the permanent magnet that will obviously induce some voltage and create electricity, right? That's how the generator will produce electricity. For 3 marks, I'm just going to write this one, that the coil is rotated, so there is a coil connected to the turbine, so it also rotates, right? And again, if the coil rotates to the magnetic fields of the permanent magnet, due to a permanent flux linkage, or we can say just due to flux linkage, voltage will be induced, which creates a current through the circuit. So we just need to write that over here. The turbine is connected to a coil. That induces voltage and current flows. Yeah, we can just see that induces voltage, which creates a current. Right? These are your 3 points for this. This is again a repeated question. We have already seen this in the previous questions also so far, right? Any problem from this part?
No problem, sis.
Okay, then again we can move on. At night, the power station does not need to generate as much electricity, such as how the output of this generator would be reduced. I can reduce that. Problem is that how can I reduce this one, right? Mm, I can use anything. Like there are actually multiple points I can use. I can reduce the strength of the magnetic field lines, or I can use actually, no, if I'm working with the field over here with this generator, it's actually difficult for me to change the number of coils and all these things. One thing I can do is that I will have to rotate that turbine slow, right? And who was rotating the turbine was rotated by steam. Steam was produced by the nuclear reactions. So I should basically reduce the rate of my nuclear fission reaction so that the total output decreases, less energy is produced, and less steam is produced, and less steam means turbine will rotate at a slower speed, and therefore less interactions and everything, right? So I'll just say that reduce the rate of nuclear fissions. So reduce the rate of nuclear fission. Now, only in this question we can write this point because it was related to the nuclear fission. If the question was not related to nuclear fission, the answer would say that use reduce the strength of magnetic field, reduce the strength of magnet. Then again, it would say use a fewer coil, fewer turns actually of coil, fewer turns in coil. And then again, we can say usually after this, we could also see that fewer turns, then reduces strength, and also use small current, right? For this question, I cannot use current because I was not using current to generate the initial rotation of the turbine. I was using nuclear energy to rotate the turbine. That's why I'm going to reduce the rate of nuclear fission. Otherwise, if the question is not related to fission, if the question was like some like this one, they will only give you one one generators like this, because I'm inserting current into this circuit to rotate the coil, right? So for these cases, I would say that use a smaller current through the coil. A smaller current means that the smaller magnetic fields will be present around the coil, and smaller magnetic field will then interact with the magnetic field of your permanent magnet. Therefore, flux linkage decreases, and obviously the current flow also decreases, right? Or induction also decreases. But as we are working with nuclear reactions with this question, so I'm going to not write about that current. I'm going to directly write that reduce the rate of your nuclear fission, and that will indirectly reduce the entire current output or electricity generation output. And the generator produces alternating current over here. Describe the differences between alternating current and direct current. This is a repeated question. This is from electricity actually, but sometimes they ask this in magnetism also. So we can see that AC changes direction continuously, but DC has only one direction. Only one direction. That stands for 2 marks. You don't have to write anything else other than this. So this is it. We're done with this question also. Then we will move on to the next one. Over it says the question is about magnets. Which of these substances is not attracted to a bar magnet? Which of these will not be attracted to a bar magnet? I understand copper. In the previous case, I saw that they will never be attracted to bar magnet. So I'm just going to write copper again, right? Cobalt, iron, nickel, they will all be attracted to bar magnets. I'm not going to label them. But this one, I think I have to draw the magnetic field lines, right? Yes, on diagram, show the shape and direction, right? We have to show the shape and the direction of the bar magnet. So this is how the field lines for bar magnet should. You can at least show 4 field lines, that's enough, and obviously the direction from north to south. Right, this much is enough. Then some bar magnets are made up of steel. Explain why steel is a good material for making bar magnet. Because steel is a what? A hard magnetic material, so it can stay magnetized for a long period of time. So we can see that so correct. Steel is a hard magnetic material, so it can stay magnetized for a long period of time. This is again a repeated question about steel, so you can memorize this one also. Any problem from this part?
No, miss.
Just 1 minute. So just 1 minute. There's actually sweat on my screen, so I cannot write directly clearly. Let me just grab my screen and then start. Yes, I'm sorry, that's okay. So we finished this one. This was a repeated question. And then after this, if we move on to this part, this one says that diagram to shows a cross section of a wire placed between the magnetic field lines. The direction of the current of the wire is out of the page. That means, you have to think of the current moving towards it, right? Out of the page means the current is moving towards you. So you have to place your third finger towards you. And what will be the direction of your field lines? It's always moving in the upward direction, right? From north to south. So this is the direction of your magnetic field lines. So towards you, upward, that means we have a force in which direction? Can anyone tell me? Current is moving towards you and your second finger should be in the upward direction. Amra, can you identify the direction of your force acting on this wire?
Miss, who are you talking? Umbra or Amna?
Amra, you must.
Okay. Will it move into the page?
No. Current is moving out of the page. Direction of the current is given. So you have to place your third finger towards you, right? Out of the page means towards. And your field lines are in the upward direction. So your second finger should be in the upward direction. So in what direction does the thumb refer to?
Is it the right?
Right? Is it right? No. Amna, can you tell me which one?
It's towards the left.
Towards the left. Amra, do we understand this? Like how it's moving
No, I
actually?
don't understand. I tried doing it with my arm. I'm not sure.
You have to use your left hand. 1 minute, I'll turn off my camera. You have to use your left hand, and this is how you have to place your hands, right? This is your direction of current, this is your direction of your field line, and this is the direction of your force. This time, this current is moving out of the page means it should be pointing towards, right? Some people place my hand like this. So the current is moving towards me, right?
Yeah.
Field line is in the upward direction, and we get the force to the left-hand side.
Oh, okay, I got it. Yeah.
So we are going to write left-hand side, and that's the direction of your force. You don't need to draw this line, by the way, the vertical line for the field lines, but only this one. Right. Draw the arrow to show the direction of force on the wire due to the field line, assume the magnetic field is uniform. Right. We just have to draw the arrow. That's now again it says that state two changes that could be made that would decrease the magnitude of the force on the wire in figure 2. Amna, can you tell me one of the reasons, like one of the few changes that would decrease the force?
Moving the magnet farther apart.
Moving the magnet farther apart. Okay, that's correct. Further apart. And Amra, can you tell me one of the reasons?
Can you say reduce the amount of charge on either or both the objects?
Charge. This is what magnetism. We don't have any charged particles here. Other than the current, this is charge. What do you think?
Can you say moving the objects far apart? Or is that already said?
No, I'm already said that, I'm going to move that magnet further apart. Increasing the distance also decreases the magnetic force. That's correct.
Wait, so can you also say decreasing the magnetic field?
Magnetic force. I want to decrease the force because that was
Yeah.
provided on this slide. You have to understand that why is the force actually there? That's because field lines are interacting, right? Field lines of the permanent magnet and field lines of the current wire. So if I'm already said this thing that I'm going to move the magnet further apart, that means it will reduce the force because of the permanent magnet. Now, if I want to reduce the force again with another point of view, this one was for that distance between the permanent magnet was increased. But other one is could be that I'm going to reduce the magnetic field lines of the current wire, right? That means how can I reduce the magnetic fields of my current wire? By allowing a very small current to flow through the wire. Small current will produce smaller field lines and therefore decrease the flux linkage and again decrease the force. Is this clear, Amla?
Yes, miss.
So we can just write that moving the magnets further apart, or I can see that now use a lower current to pass through the wire. Decreasing the current flowing through the wire, right? That's it. I can also talk about a lot of things. For this type of questions, you should memorize 4 points at least. One is that yes, moving the magnet farther, like moving the magnets farther, decreasing the current flowing through the wire. I can also say decrease the voltage through the wire. A voltage in wire. And then again, we can say that we can use weaker magnets, right? Weaker magnets will also have weaker field lines. So use or weak magnets. Right, these are the 4 mark scheme point we should remember for this question. This is a very, very important repeated question in every paper. Either in paper 1 or paper 2, you'll see this type of questions. So just memorize these 4 points entirely. That's it for this question, I think. Yeah, we don't have any questions from this part. Then if we move on to this question. A device called a metal detector is used to find metal buried underground, and we have to. This is a receiver coil transmitter. This is how the circuit looks like with electronics transmitter coil. So this is why there is a magnetic field around the transmitter coil. Why there is a magnetic field around the transmitter coil? Because no current was flowing through them, right? Because of a current in the coil, there will be a magnetic field. Because the current in the current carrying coil acts as an electromagnet. So we can say that current carrying wire or coil acts as an electromagnet. Right? That's the first part. Then the cell applies, so cell supplies direct current. The electronics in the diagram 1 show the direct current into alternating current diagram. The electronics in diagram 1 change the DC into AC. Okay. So we are supplying AC from here, but this one converts that AC then to DC and describe the difference between direct and AC, right? I think I've already written that in the previous part. In this one, yeah, this one. This is the difference between your DC and AC. There's no point of writing the same question or same answer again, so I'm just going to copy this and paste it. Answer is same everywhere. For direct and alternating current, answer is same. So I'm just going to paste my answer for this space. Okay. Now after this, if I move on to the next part, it says the alternating current is supplied to the transmitter coil. Diagram 2 shows a gold ring in the soil below the metal detector. Explain why there is an alternating current in the gold ring. Sorry, alternating current in the gold ring. Right. This is because of your like you're kind of working as a transformer. This is like your primary coil where it is directly connected to your source. Okay, this is like your primary coil, right? And this is acting like your secondary coil. In this case, the primary coil is actually producing changing magnetic field lines, right? So we have field lines around this primary coil, which is now changing. Every time the direction of the magnetic field line changes as soon as the AC current supply changes its direction. So whenever the changing magnetic field line from the transmitter cuts the secondary coil or ring, a voltage will be induced. This is induced according to Lenz's law, but we don't understand Lenz's law now. So you just always have to understand that whenever this metal detector transmitter and the ring were not connected to each other, right? Then how would that ring will have a voltage in them? That's because of a transformer effect. And in transformer effect, what we see is one coil is connected to the supply and the other coil is not connected to the supply. The coil that is connected to the supply is considered as a primary, and the coil that is not connected to the supply is considered as secondary. So in the primary coil, we have AC power supply and AC current. AC current changes its direction continuously, and AC current changes its direction, the magnetic field line produced by the transmitter will also change its direction. So this changing magnetic field line will cut with the will get they will actually interact with this secondary coil, and that will induce a current in the secondary coil, right? Or that will increase a voltage in the secondary coil, and that's your EMF, right? That's how we create the EMF of a transformer. This type of effect is known as the transformer effect. And this is again a repeated question that I'm going to write over here. Right, so for your transformer effect, you have to memorize these points. The AC continuously in the right. That's a repeated question, and you guys should memorize this anytime. Any question from this transformer effect?
No questions, miss.
Please, so we move on to the next one. That's for the loudspeaker. Again, I repeat it. Right. They're asking diagram 3 shows the circuit for the receiver coil, and there's a receiver coil and the loudspeaker. As a result of the alternating current in the gold ring, there is an alternating current in the receiver coil, and explain how an alternating current in the receiver coil causes a sound to be emitted from the loudspeaker. Again, this is a repeated thing. We're going to see that alternating current in the loudspeaker creates a changing magnetic field line which interacts in the loudspeaker, causing a force to be produced on the loudspeaker pole. So this, as the field line changes, the direction of the force also changes, creating a vibration, like vibrating force on the loudspeaker. That vibration causes vibration of the air particles, which creates longitudinal wave or sound basically, right? So we just look at all those things. That alternating current Alternating current in the loudspeaker forms changing magnetic field lines. Which interacts with the permanent magnets. In the form of loudspeaker. Seals causes the force direction to change. Right. This vibration is passed on to the air particles. To generate sound waves, right? That's the final answer. Like any problem from this part?
It's chemist.
These are the marks confirmed by the. Okay, then if we move on to the next part. This one shows the direction. The diagram shows some equipment for the physicist. I think there's a typing error or something. I don't know. Physicist used in an investigation in 1820. Diagram 1 shows the position of 8 compass needles around a wire with no current. No current in the wire. The compass needle line up with and show the direction of the Earth's magnetic field lines. And diagram 2 shows the direction of the compass needles when a current is in the field line. The current is now in the wire, and this explains why the compass needles turn when the current is switched on. Because when the current is switched on, the wire have some magnetic field lines. So those provides the direction of the magnetic field lines around the current, right? So they're giving you 2 marks. That means it should be that current provides a magnetic field line, and 2 marks, right? There's just 1 point. Yeah, current provides a magnetic field line. You can just write that current provides the magnetic field lines. So the compass needles line up along the field. Along the field lines, right? This should be a final answer. It can be considered as a repeated question, but it's very easy. So I don't think you guys have to memorize this part. Then again, use evidence from the compass needles and diagram 2 to draw on diagram to the shape and direction of the field lines, and that's it, right? Okay. So I can see that we can create a kind of circular field line in this case. Right, this type of circular field line is okay to fit in. And then again, what will be the direction? Always remember the needle points towards the south pole, always, right? So the needle always point towards the south pole. So we can see that the needle is pointing in this direction. So this is your direction. Oh, wait, no. The black part is actually the needle, right? The needle is pointing in this direction. So this is your direction of your current, the magnetic field in the current carrying wire. That's a clockwise direction, right? What we understand from the clockwise direction, if you use your right hand grip rule, I'll be able to understand if the current is moving into the page or out of the page. Can anyone tell me in which direction the current must move in this case to create that clockwise field line? Right hand grip rule, use that.
Into the page.
Into the page, right? Yes. Because if you move our hands in the clockwise direction, the other 4 fingers in the clockwise direction, my thumb will always point into the page. Amra, do you understand this?
Yes, miss.
Okay. Then if we go there, suggest what happens to the magnetic field when the current in the wire is reversed, right? I know the current will be flowing in the anti-clockwise direction then, right? That's it. If the current is going to change its direction or anti-clockwise direction, you can see that change its direction to anti-clockwise. I can just change its direction, that's it. Is this the last? The current in the wire is turned off. Diagram 3 shows the wire placed in a uniform field line this time. The current is now switched on. Draw an arrow to show the direction of the force on the wire. This time, whenever I'm only working with a current carrying wire, I have to use your right hand grip rule, right? And whenever I'm working with a current carrying wire with a permanent magnet, I have to use your Fleming's left hand rule. So we can write 1 minute. We're using right hand grip rule as I'm working with just current carrying wire. Thus, current carrying wires have to use your right hand grip rule. And if I'm using your current carrying wire with permanent magnet, just 1 minute. That's your Fleming's left hand rule. Now I have to use your Fleming's left hand rule for this thesis. Left hand rule. Okay, if I understand that, if I start here, draw an arrow to show the direction of the force acting on the wire, I have to think of this as current is moving, like this direction actually means current is moving like towards you, okay, because you assume you're standing over here. So current is moving towards you, field lines are moving from north to south, from north to south. So towards you, north to south means an upward force will act on the wire, right? Amna and Amra, do we understand how an upward force is acting on the wire?
Miss, I'm not that sure. I'm not too sure.
Mhm. Just think of this time again as you are standing in front of the magnet, right? So if you're
Okay.
standing in front of the magnet, then what happens? You have to use your fingers again in this manner, right? And if I'm using my fingers in this manner, then again, I am considering that uh, current is moving towards me, right? If current is moving
Okay.
towards me, so I have to consider thinking, I have to reposition this finger to
Mm.
this side, right?
Okay.
So if my that finger is moving towards me, field line is moving from north to south, we get an upward force in this case.
Yeah.
Right? So that's why we get upward force. Is this clear now?
Yeah, I've got it.
So we have upward direction. That's it. This is for 2 marks. Then again, they are saying the power supply in 3 is replaced by an ammeter, and when the wire is moved, the current is detected. Okay, this time it means that previously, I was providing some electricity to this wire. Then we have some magnetic field lines of wire that is interacting with the magnetic field lines of the magnet, and that created some external force on the magnet, right? But now if I'm going to replace the power supply with ammeter, that means now I'm not providing any current to that wire. If I'm not providing any current to that wire, that means you don't have any current carrying wire. It's just a wire. And whenever that wire moves, we still have the magnetic field lines of the permanent magnet, right? So whenever the wire itself is interacting with the magnetic field line, that also creates a flux linkage. And this flux linkage will induce a voltage in the wire. Voltage induction means obviously a current will be produced, right? So we just have to write this down. Explain which direction. Oh, I don't have to explain that. The explanation is over here. In part 1, they're asking that in which direction the wire should be moved, right? In between the field line to produce a current in the wire. You have to understand that in this case, the field lines were kind of in this direction from north to south. So your movement should be perpendicular to get the maximum effect of this case, right? So you just have to write up and down, uh, or we can write vertical motion through the field lines or cutting through the field lines. Up and down, vertical motion. Okay, which is up and down motion, cutting through the field lines. Right. Then again, explain why a current is in the wire when the wire is moving in the magnetic field. Then I have to write that thing that as the wire moves, it cuts through the field line, which causes flux linkage that induces a voltage across the wire. And since the wire is a complete circuit, that voltage gives a current. So voltage gives a current, right? That's your final answer. By the way, this is again a repeated question here. If you're done with this, then we'll move on to the next question. Can we just wait for a few minutes for the prayer to end in my side? Okay? Just a few minutes. Okay, so we are starting with this child 24-1 question 2. Diagram 1 shows magnetic field lines between two poles, strong bars. Add labels, which basically have to identify the pole. I understand field lines are going from the left to the right. That means this is your north pole, and this one's your south pole. Right, that's it. Then the bar magnets are made up of steel, and give one reason why steel is a good material for making bar magnet, because they are magnetically hard material. I don't have to write about that. They will hold on to their magnetic property for a longer time because they're only giving me 1 mark. So I'm just going to write because they are magnetically, or I can say magnetic because they are hard magnetic material. Materials. Explain how in diagram 1 they show uniform magnetic field line. Repeated question. This is what we started with the very first question of this worksheet. The field lines should be straight, parallel, and evenly spaced. So that's what I'm going to write. That the field lines and evenly spaced, right? This is for 3 marks, but obviously we can write 1 maximum marks for it. Then if we move on to this one, diagram 2 shows the metal wire being moved downward through the uniform field line. We have the metal wire and it is moving downward through this field line. Between the poles of the seam bar magnet, the orientation of the magnets have not been changed. The orientation of the magnet have not been changed means that this is still the north pole and this is still the south pole. Okay. So we have this direction of a field line over here, and if I see that, in this case, if you're this time, what are the informations given? Force and field line is given. I need to find out the direction of your current, right? So in this case, what will be the direction of your current? Give a reason why a voltage or no. Not the direction of your current. It says give a reason why voltage is induced when the ends of the metal wire as it moves between the poles of the magnet. Similar, obviously this time the magnetic field, the wire is going to cut the magnetic field that will create some flux linkage and eventually will induce voltage. So I just have to write this one, that it cuts the magnetic field line and yeah, just cuts the magnetic field lines is enough as they're only giving you 1 mark. That much is enough. And state two changes that could be made to this arrangement that would increase the magnitude of that induced voltage. I can move the wire faster. I can use a stronger magnets. I can move the magnets closer. And I can also turn the wire into a coil. Turning the wire into a coil means it will have a more surface area, more field line, like more interaction with the field lines, and therefore increases the flux linkage. So you guys should memorize all the 4 points with this type of question. Was that turn coil? So you turn wire into coil. Then again, turn wire into coil, and what else? Turn the wire into coil. Move magnets closer. Use stronger magnets. Move the wire fast, right? These are the informations that you can write. Any problem from this part?
No problem, sis.
Okay, so in that case, just